So let's start off our section 4.1. In this we're looking at antiderivatives. Antiderivatives. And derivatives, yep, okay. And indefinite integrals. They're the same thing, indefinite integrals. And so in this case, what we're looking at is doing the inverse of derivatives. So we've got all these nice derivative rules, and if what I tell you is, for instance, that f prime of x is equal to 2x, then I could ask what was or what is f of x. And I'll put an if here. If that's the case, then what is f of x? And here's where you have to be a little careful. So hopefully you would look at that and say, oh yeah, f of x is x squared, right? Because if I take the derivative using the power rule, then I bring down the 2 and leave a 1, I'd get 2x. Well, we aren't actually quite right. Okay, because there's a whole family of functions that would make a derivative of 2x, and it could be any constant, right? Because as we take the derivative of this, so if I want the derivative of f of x with respect to x, then that's the derivative of x squared with respect to x plus the derivative of a constant with respect to x. But that is 2x plus 0, no matter what that constant is. That constant could be a billion, and I would still get that. And so that's really the big thing we have to remember when doing antiderivatives is there's always this possibility of a constant hanging around, and other than that, mostly, we have one major rule, power rule. Okay, so if we have f prime of x is equal to x to some power p, then f of x must have been, well, remember when we took the derivative, we subtracted 1 from p, so now we need our p plus 1 in order so that when we take that derivative, we bring that down to a p. But since there's no constant in front of there, actually we had to divide by p plus 1, and so this is true for every p not equal to -1. And so proof. Okay, let's start with the derivative of x to the p plus 1 over p plus 1 with respect to x. Well, I can factor out the 1 over p plus 1, and then I just have the derivative of x to the p plus 1 over dx there. So, and then using the power rule of differentiation, I get 1 over p plus 1 times p plus 1 times x to the p plus 1 minus 1. And so then that is equal to, well, p plus 1 over p plus 1 is 1, so that goes away, and p plus 1 minus 1 is just p. And so, yep, the function, the antiderivative of x to the p is indeed x to the p plus 1 over p plus 1. So, if I'm told f of x equals x squared, and I want the antiderivative of that, so, okay, the antiderivative is, now this is not a typical, this is not a standard notation, but often what people will do is, if little f of x was the original function but we want the antiderivative, they'll go with an uppercase letter, so uppercase f of x equals x cubed over 3 plus an arbitrary constant. Okay, and I guess actually I forgot that in our power rule up here. I was a bad person. I should have had the plus c on the end of that, right? Because any antiderivative, we can always add that constant, and in the proof, well, that would be what I did up here. So yeah, I messed that up a little bit there with the constant, but remembered it down here. So, so our antiderivative would be x cubed over 3 plus c. Now, let's look at technology with this. Sage math is pretty good. It doesn't take much to find the antiderivatives there. So let's look here at what I would type into Sage. So we have var x to define a symbolic variable. I say f is x squared, and then I use the uppercase f. Again, it's not truly a standard notation. Just because you see an uppercase doesn't mean it was an antiderivative, but it might be. And then f dot integral, and we'll go back to talk about that for a moment, of x, so with respect to x, and then show f. And notice what we get down here, 1/3 x cubed. Sage math does not add the plus c. Okay, you need to remember that. We always need that plus c on there, or it's not quite correct. So Sage math does a nice job, except that it leaves off the arbitrary constant. Now, if you go to Desmos, and again, we'll see this notation in just a second. I'll mention that. But here, f of x is our x squared. And if I type in int, I get this funny sign here that looks like a script S. Maybe should be on a violin or something. And then I say, well, what do I want the antiderivative of? F of x, and then dx tells it, just like in Sage, well, what's the variable? It's x, so dx is the variable. And notice I get a big warning sign over here. It says integrals must have, I can't, you can read it, but I can't read it so well. Must have upper and lower bounds. Okay. So there you go. It needs upper and lower bounds. Whoops. Get rid of that. Put that. Just go back. There we go. No. It's all very confusing to me. Okay. Now, so what I can do is I can give it a lower bound and upper bound and then add my constant in this way. But notice I said 0 to x and then f of z dz, and of course I don't get a formula. I get, well, maybe I get, there we go, I get a function. And see there, it looks a lot like x cubed, so it's probably 1/3 x cubed. We can type that in to see. But then there's my arbitrary constant, which if I grab hold of it and move it around, notice, see all those functions that just move up and down the y-axis have an antiderivative of 1/3 x cubed. And so here I'll just type in x cubed and then divided by 3, and there it is. And if I go back here and make that, oh, I don't know why I can't, come on. Huh. I don't know, it's not letting me edit that. So, let me see if I can, there's that. I had this trouble before. It's really tough with my stylus to get that to stop right where I want it. So, so I'll just go like this, minus 0.2. There we go, and then the one is on top of the other, right? So they are the same function. Okay, there's the green one. Now I'll try to get that back. Yeah, the stylus stuff with this thing is less than perfect, but there we go, and it's back. Okay, so those are that same function, one x cubed over 3, or 1/3 x cubed. So we can get that in Desmos, although not a formula, and we can get it in Sage Cell here, but that formula is lacking our arbitrary constant. And so, here, going to the notation, right, it's kind of a pain to write the antiderivative is. Why not just a simpler notation like things like f prime and so forth? Well, that's what we have, is that we could write that our f of x is, and you do that sort of S-shaped thing, that's saying I want an integral or antiderivative. So this is an indefinite integral or antiderivative, and then of what? Well, f of x, and then, well, what's the variable? X. Now, that's pretty clear in this case, but on the other hand, if I wanted the antiderivative of cx squared like that, well, is c the variable or is x the variable? Okay, you and I would probably look at it and just say, oh, well, x is obviously the variable. Yeah, but how does the technology know? Okay, or how does somebody else know if this is out of context? And so we toss that in, the dx, and we'll see later where this notation kind of came from, but this is an antiderivative. So, as far as rules, you need the power rule. Beyond that, it's really just practice with things. So, for instance, if I'm told, I've got f of x is sine of x, and then I say, well, what's that antiderivative of sine of x dx? Well, remember that when I take the derivative of the cosine, I get the sine. Sorry, when I take the derivative of the cosine, I get the negative sine. This isn't negative, and so this is actually negative cosine of x plus an arbitrary constant. Okay, so that's, things like sines and cosines, you have to be careful, and it's a matter of practice. You do lots and lots of practice. We have tables and so forth. So your textbook on page 246 has a bunch of tables and rules. And beyond that, though, it is practice, and I can still mess them up. I've had a lot of practice, but I probably don't mess them up near as much as my students. So this is the idea of antiderivatives and our symbol to say that's what we're doing. And I think that's good for this video.